Welcome. Hi. Welcome to day 21. Today, I wanted to give you some deeper insights regarding identifying patterns. It is crucially or critically important to have to get habituated with the process of identifying patterns in physics. It is really important. And for plus two students, it is really easy to identify patterns between various topics starting from plus one, plus two, and uh, including many chapters and topics. So I just wanted to uh, give you a clarity related to this by uh, taking one example as of now. So the example I am taking here is that of electric dipole and magnetic dipole. Let me directly come to the presentation. Now, see, this is a uniform electric field. Uniform electric field. How can we identify that this is a uniform electric field? See, in the case of a uniform electric field, the field lines are unidirectional, equidistant, and uh, equally spaced. That is the peculiarity of uniform electric field. Now, whenever you see this kind of a uniform electric field, what all things you will be able to read between the lines? That is my question. See, normal students know this is a uniform electric field. By seeing such a uniform electric field, what will be you reading beyond this image? Obviously, we can understand that there will be a positively charged plate here. That is one situation. Or there can be or there will be a negatively charged, uniformly charged plate here. Second possibility. Now there is a third possibility as well. See, you place both positive and negative plates like this. See, let this be a positively charged plate and this be a negatively charged plate. In this case also, you will be having or you will get this kind of a uniform electric field. Strictly speaking, this will not be perfectly uniform. At the end region, the field lines will be acting like this. Slightly, 1 second. Yeah. It will be slightly bulging outwards when it reaches the end. But obviously, in the mid region, the electric field will be uniform. The field lines will be parallel, equidistant, and unidirectional. Okay, that's it. Now, let me clear this one. We are considering a uniform electric field, and a dipole is placed in a uniform electric field. What is a dipole? As we know, dipole is two equal and opposite charges separated by a small vector distance. And we have learned about this concept starting from first year chemistry onwards. Dipole moment and its unit, everything we have learned. And we are familiar with certain molecules which are which possess dipole and dipole moment. Example, hydrochloric acid, HCl molecule, NF3 molecule, NH3, ammonia molecule, water molecule. There are several molecules which possess electric dipole. So here, the two charges plus Q and minus Q is given. And one thing we need to understand is dipole length is the length between two equal and opposite charges. Here, positive charge is plus q, negative charge is minus q. Distance of separation, it is given by the pink arrow. And it is a vector quantity, dipole length. And usually the dipole length is measured from negative charge to positive charge, unlike in the case of an electric field. In the case of electric field, we draw the electric field line starting from positive plate or positive charge and terminating or ending on a negative charge. That is the character of electric field line. And electric field line is defined like that also. It is the path along which a unit positive charge would move if it is free to do so. See, imagine you have a positive charge. You are releasing it. Or now, when you release the positive charge, it is free to move by its own. It is having the freedom. In such a case, if it is moving, what does it mean? See, you are releasing the positive charge from rest. Now, if it is moving, what does it mean? It means there acts some external unbalanced force according to Newton's first law. Because every body should continue its state of rest or of uniform motion unless it is acted upon by an external unbalanced force. Or on the other side, the charge would have remained at rest or continue in its present state if there was no external force. So whenever you releases the positive charge, it starts moving or it is getting accelerated. What does it mean? At that region, there exists or there exerts some force on this particular charge. And as a result of that force, only the charge is getting accelerated. That is what we need to understand. So now, this situation, you consider this situation, an HCl molecule or an ammonia molecule or a water molecule. It is having a dipole moment of its own. So natural tendency of the dipole will be the positive end of the dipole will remain as far as possible from the positive charge. See, where is the positive end of the electric field? This is the positive charge from where electric field is getting generated. And it is acting towards the negative plate. So, whenever the positive charge is remaining here, the repulsion by the positive plate will be the minimum or least. And in a similar way, whenever the negative charge is remaining closest to the positive plate, the attraction will be maximum, and on the negative charge, the repulsion due to the negative plate will be minimum. So this is the most comfortable position of the dipole when it is placed in an electric field. In two ways we can define it. See, whenever the positive charge is remaining here, it is at a maximum distance from the positive plate and it is at a minimum distance from the negative plate. Most comfortable place. And the same is true for negative charge also. So this is the situation. Okay. So we did understand two things. In the case of electric field, we are drawing the field lines starting from positive to negative. But in the case of electric dipole length, we are measuring that vector quantity starting from negative charge and moving towards the positive charge. That is the electric dipole length. So here the pink arrow represents the dipole length 2a. Okay. Now I will be showing. Now this is the most comfortable position. Now think about a situation. I am rotating this dipole towards the clockwise direction. I am trying to rotate it. Just like this one. Okay, see this. I have rotated the dipole through some angle theta. Now this one makes an angle theta with the electric field. Now see, the positive charge, it is not at a maximum distance from the positive plate as in the first case. It came closer to the positive plate. Similarly, negative charge, it is also not at the farthest point from the negative end. It is also came closer to the negative plate. So what will be the natural tendency of the dipole right now? Right now, the tendency of the dipole, we can consider two possibilities or possibilities simultaneously. The tendency of plus Q will be to move, 1 second. Yeah, it will be trying to move towards the negative plate. At the same time, the negative charge will try to move towards the positive plate. That will be the natural tendency. Then what will be the force here? Here it will be QE, which is equal to force, or more specifically plus QE, because it is acting towards the upward direction. But at the same time, the force acting on minus Q charge will be minus QE, which means it is acting towards the downward direction. So both the forces are equal. Because both the charges are equal, those are placed in a uniform electric field. The strength of the electric field is constant throughout the electric field. So in this particular case, the forces acting are equal but opposite in direction. Now, you think about these two forces. These two forces are equal, opposite, but non-collinear. What do you mean by collinear? Linear means acting along the same line, or line of action is same. But here the line of action is not the same. There is a separation. How much is the separation? We can calculate it mathematically using this particular image. See, I have drawn a right-angled triangle with the dipole length coming as the hypotenuse. This is hypotenuse, 2a, dipole length. Okay, now we know that this angle is theta. It is already defined in the second image. Now, if this is theta, this angle will definitely be theta. Alternate angles. Okay, now what is the perpendicular distance between the two forces? The two forces are QE in the upward direction, QE in the downward direction. What is the perpendicular distance? This is the perpendicular distance. Now, by the principles of trigonometry, we can arrive the length, this particular perpendicular length, to be 2a sine theta. Okay. Now, what about the torque acting here? Here, see that there are two forces, equal, opposite, but non-collinear. So these two forces will constitute a couple which will try to rotate the dipole. See, I can demonstrate it using my marker in my hand. You consider this. See, this is the position. Now there is a force acting at this end towards the upward direction, and here there is a force acting in the downward direction. Okay, now these two forces will try to rotate the dipole along this particular direction. That is what is happening here. So what is the magnitude of torque acting here? Torque can be obtained by taking the product of one of the forces, that is QE, into perpendicular distance between them, that is 2a sine theta. Now, from the earlier concepts, you are clearly knowing that, you will be clearly knowing that 2 times 2a is nothing but the dipole moment of the dipole. So we can substitute that value, PE sine theta. It is the torque. Now, torque is a vector quantity, and this is what I want each one of you remember or internalize with clarity. Whenever there is a sine theta appearing in any equation, physically it means that there is a chance for that equation to be written as the cross product of two vectors. Here, what are the vectors? One is electric dipole moment. Second one is the electric field. Both are vectors. Okay, so we can rewrite this equation as torque is equal to P cross E vectorially. This is the vector representation of this particular situation. Now, one more thing we can do. See, in order to rotate the dipole from this position to this position through an angle theta, you need to do work because you are rotating it against the normal tendency. Normal tendency of the dipole is to remain parallel to the electric field, but you are trying to rotate it against the natural tendency of the dipole. So you need to do work, and the work which is being delivered by the external agent, here it is you or me, that work done will be stored in this particular dipole as its potential energy. Potential energy is the energy possessed by any object by means of the configuration or state of strain or position. So here it is under a state of strain because the natural tendency of the dipole is to stay parallel to the electric field. You are disturbing it. So it is having a tendency to go back and remain aligned parallel to the electric field. That is a natural tendency. So here, whenever you are rotating it through an angle theta, the work done by your end will be stored in that particular dipole as its potential energy, or more specifically, electrostatic potential energy. And the potential energy here is given by, potential energy U is given by minus P dot E, or without vector notation, you will be able to write it as minus PE cos theta. That is the equation to find out the electrostatic potential energy when you are rotating the dipole in the electric field. Okay, so this is the situation about an electric field. Now we will be able to see the similar situation when you are considering a magnetic field. Here, let the pink lines, pink arrows represent a magnetic field represented by B vector, and this be a magnetic dipole, that is simply a bar magnet. Okay, now here also you should understand that here there will be a magnet whose north pole is placed here, and there will be a south pole placed here. That is the meaning. Whenever you see a uniform magnetic field like this, you should understand that at the point from where the arrows are originating, there will be a strong north pole, and where the arrows are getting terminated or directed towards, there will be a south pole. Now, the magnetic dipole or the bar magnet, it will be positioned like this. Its north pole will be pointing towards the south pole of the magnet, or north pole will be nearest to the arrow direction. Okay, and south pole will be on the other side. This will be the tendency of the magnetic dipole. Now, in this position, it is at a most comfortable position because north is near to south, and for the south pole is near to the north pole. So the repulsion is minimum and attraction is maximum. So it is in the most comfortable position. Now think about rotating this dipole. Second, I wanted to move this. Yes, here it is. Now I wanted to get this. Yes. Yeah, this is the normal position of the dipole. Now I am trying to rotate it through 45 degree. See what I did? I am rotating it here. So here the whenever you rotate it through an angle theta, second, let me take the color. Okay, theta, again here the force is plus qm. Here qm represents the pole strength of the magnet. Pole strength of the magnet, not the charge. Okay, magnetic pole strength. And when you multiply this magnetic pole strength with B, you will be getting the force acting on the north pole, which is the repulsive force. Similarly, here this is minus QM, which represents the pole strength of south pole. And here also a force is acting, which is given by minus QM into B. And normally this dipole length is 2a. Now two equal and opposite forces. Equal, opposite, but non-collinear. This will constitute a couple. Moment of that couple is torque. And here torque is given by one of the forces, that is Qm into B into the perpendicular distance. This distance, again this distance, perpendicular distance will become 2a sine theta by the trigonometric identity. Now again 2m times 2a will give the magnetic dipole moment, magnetic moment. So torque is equal to m into b into sine theta, because magnetic moment is represented by small letter m usually. Now you think about this, mb sine theta. In that equation also sine theta comes. So remember the thumb rule. Whenever there is a sine theta appearing in any equation, there will be a strong chance for that equation to be represented as the cross product of two vectors. So here torque tau is equal to m vector cross b vector. So this is the torque. Now again, in rotating the magnetic dipole through an angle theta, you have to do work against this torque, because torque is trying to bring it back to the most comfortable position or the equilibrium position. But you are doing work against the torque, and that work done by the external agent, here it is you or me, that will be stored in the magnetic dipole as its magnetic potential energy. And here also that potential energy UB can be written to be minus m dot b. See the similarity. There it was torque was P cross E. P was electric dipole moment and E was electrostatic field. Here m cross B. M is magnetic dipole moment and B is magnetic field, strength of the magnetic field. Similarly, there the potential energy, electrostatic potential energy was minus P dot E. But here it is minus m dot b. So my suggestion to each +2 student is try to identify these kind of patterns appearing in many topics in physics. This will help you to crack many entrance exams, or let me put it in this way, this will help you to solve many problems which are coming both in board exams or in entrance exams. This kind of clarity will help you to to minimize the load of learning. You will start the process of learning with enjoyment. You will be able to connect the dots. Each of the foundational stones are in place. So the foundation on which you are building the concepts will be really strong, which will help you to have a solid foundation and solid conceptual clarity to move further on your journey. So my request is, if you are a diligent student who wanted to know more details about learning physics in a proper way, with lots of fun, joy, excitement, and enthusiasm, and with real internalization, real passion, then I would like you to attend my free webinar called Physics Made Easy. Okay. So it is a free webinar, 2-hour long webinar, in which I will be revealing many relevant information, including various studies and statistics, which will help you to identify the gaps and cracks those exist within our broken education system, especially when it is related to the mastery of a beautiful subject like physics. So it will help you to sort out a solid roadmap towards physics mastery. So you will be able to find the link to register for the free webinar by looking at the description of this particular live video. So I would like each one of you to share your thoughts below this particular video. Was this useful? And what is your thought about this concept of identifying patterns? If you have identified any other patterns like this, please give those also as the comments below this particular video. So I am signing off from this today's live video. So really happy to see you here, spending time with me. So bye for now. Thank you.